Today I'm going to introduce the Navier-Stokes equation in vector notation. I think vector notation is pretty useful when we're talking about numerical modeling because a computer can better, I guess, read these equations, or we can it's better to say we can input the equations into the computer easier, or we can write down a numerical form for our solver in a more simple way in a one line. So previously we talked about this form, which is the del operator notation, where del is this one. We would call it del. And basically we use this u vector, which is the thing on top means vector, and then we define our u in the x direction, v in this is u in the y direction, and u in the z direction. So more generally, we should actually write the velocity, u is for velocity, like this. So we have, the u in the x direction, u in the y direction, u in the z direction, and I is the x direction, right? J, and then k is z. So you write it like this, and this is really an equation. This equation will turn into an equation like this. It'll be dux dt, duy dt, duz dt. Right? This is one equation, this is another equation, there's another equation. The pressure gradient will, be here, like dp dx equals -1 over rho dp dy, etc. Right? So we use this del operator, which is basically looks like this. I'll write it down. So let me just move this around. This goes here. This is actually next. And then this, I'll just write it in purple. This is ddxi plus ddyj plus ddzk, right? Okay, that's nice. Yeah, it's one line, but we'd have to go into a computer and define this, and in a computer it's usually nice to write things where you have like some sort of letter like I, and you can set it equal to 1 or set it equal to 2, and it will give you a different equation. So going to the vector notation, which I'm not exactly sure, but I believe this is also called Einstein notation or something like that, but I'm not quite too sure. Vector notation is what I'm going to call it. And so basically we define this thing called ui, where I could be equal to x, y, or z. So really the things that ui can contain could be ux, uy, uz. On a computer we could call it u1, u2, u3. So I guess, better way would be ui for I in x, y, z, or we could say I in 1, 2, 3. That will just be our 3 dimensions, our x, y, z dimension. We can just number like that. So in a computer, we just keep track of the fact that 1 is that dimension. We also have xk, which would be, you would have x dimension, y dimension, and z dimension in there. So it's kind of like ui, but that's for velocities. This is just for dimensions. You could also put this is longitude, latitude, and z in xk as well. And so this is how we're going to write our equation. So the total derivative, like ui, for example, that would be like you'd set I equal to 1, and you get your ux equation, dux dt. You set your I equal to 2, and you get your I equal 2, and you get your du2, or otherwise known as duy dt. Sorry, there's a capital D, or not. It's a D, not a partial. Okay, and then same thing here. You get your dp dx, right? Your dp dy, partial p partial y. Sorry, partial p partial z on different lines. That's different equations. So that's really neat. And then now we see, okay, where does xk come in? Xk occurs on a single line. It doesn't cross over lines. So the I, you can think of this dimension when you're thinking of like equation 1, equation 2, equation 3. That's the I direction. K is along this direction. So whenever you see this, you add up along all k. So like du dxk will equal to be du d x plus du dy plus du dz. That's what that's going to do. So in this equation, you have 6 equations. You have on one row, you have it loops through x, y, and z. So there's like the x1 plus the y1 plus the z1. Next one also is x plus y plus z. So there's 9 equations. There's another one too. And then if we look inside of the total derivative, we also have this kind of thing. This is how we'd write advection in vector notation. You basically loop through, you add together this equation 3 times, and then you also do it along the I direction. So for I equals x, we would have, dux, and then uk, we'd also have ux, and then dx, but then we'd also have plus, again dux, but it's dy this time, which is x2, and then this is uy, and then you also have uz dux again dz. So again, that's also, I think, 9 equations, or not 9 equations, but 9 things, basically. 9 separate, terms, that's the word, terms, 9 terms. So anyways, and then, and I forgot to mention, you want to add gravity in there, we have to use this Dirac delta, basically, this delta, which it's gonna be, let's see, k. So I think we can define this however we want. Maybe it's better to not mix up with the let me think. I think we could call this I, maybe diz. Right, yeah, we can do that. So basically what's going to be is, and I forgot to correct this, if the I you enter is x, for example, then you have delta x z, but then x does not equal z, you see here. X does not equal z, so this will end up being 0. So gravity only occurs when we have delta zz, then it equals 1. Then we'll just have our subtract gravity in that equation. So we could add on, if we were talking about horizontal gravity or something crazy like that, this notation would become something like if I is equal to maybe x or z, So, but obviously we don't have that in our world. But this notation is basically extremely flexible. So yeah, I don't know if this will come into handy in the future, but I've been starting to notice a lot of numerical solvers for non-structured grids. They kind of use this i's and k's as sort of like a vector notation for defining how their solver works. So it could be useful in the future, but it's just nice to know that there's another way of thinking of things. But I like this notation because it's just kind of prettier. You don't have all these weird subscripts kind of getting in the way of my vision. This one's just, it's a nice little upside down triangle. and you just have to remember a few things like this. So yep, I'll hopefully have a video on non-structured grids in the near future. Okay, stay tuned. Thanks.